Hey everyone, thanks for joining in. I'm Charan, working as tech lead at ShareChat. As part of this presentation, I'll be covering how we at ShareChat are tackling the problem of engagement counters with Kafka streams and ScyllaDB. Through this presentation, we'll briefly go over what ShareChat is, the scale around which we operate, and why did we choose streaming as a solution, right? And few requirements around the problem that we had, and architecture that we currently have in place, and few internals around it, and how ScyllaDB is helping us in solving a part of the problem and our experience so far uh, with ScyllaDB. So ShareChat is India's largest homegrown social media platform, which offers content creation and consumption in 15 Indian languages. And we are on our path to build an inclusive community that encourages and empowers each individual to share their journey and valuable experiences with the comfort of their native language. And currently, we are operating at a scale of 125 million users a month, and our users end up sharing content and experience, which add up to around 1.3 billion plus shares a month. And on an average, typical user spends an approximate of 31 minutes on the app. Right? Yeah, so that is ShareChat. And to understand what engagement events are and the criticality around it, right? So while serving content to our end users, we collect a lot of events around the way they interact with our app, and these include view events as well, as in which post the user had viewed, and if they had found that particular post engaging by liking, sharing, or commenting over that post. So it is sort of evident that we do capture a lot of events at multiple post level and also around multiple levels of engagement. When I say engagement, again, it is the combination of likes, shares, comments, etc. And the scale of engagement events alone ranges from 370K to 440K ops per second. And so these are also critical in nature, as we want to show these back to our users on the feed as a feedback mechanism. And they also play uh, some role in the process of curating the better content for our users using some of the data science and machine learning models. And when the basic problem, the question arises like, why did we go with streaming, right? And if we were to look at the other paradigms that are available for us to handle this particular problem, the first one is the request response, right? Well, it's the lowest latency option with frequent updates reaching the database, and with the magnitude of scale of events that we have, it is going to be a bit too much on the database with more connections and unnecessary writes or updates on the DB. And why did I say unnecessary writes or updates? Because, like shown over here in the slide, 12,500 and 12,599 are the same because we end up shortening the particular number and show it as 12.5K likes on the feed. Right? So the updates happening from 12,500 to 12,599 doesn't really have to be in real time, and this only grows with the order of the number, right? And it is sort of evident now that in order to reduce the database calls, we could aggregate over set of events uh, over some time and then make a single call, or maybe reduce number of operations on the database. Then comes batch processing, right? It is the high throughput option. Here we set up a process which runs every certain interval, executes on the data, and that was available since last execution. Uh, and this comes up with different set of problems for us, uh, as in uh, given that like we are running this particular process every certain interval, uh, we will have some stale data for the early engagement. As in, for a post, we just started to receive the engagement, which is again the combination of likes or how the user is engaging with that particular post, right? The updates are going to be crucial, as in there is not going to be any shortening happening of the number uh, for a while on those counters while showing them on the feed, right? So then we have the stream processing, right? Well, it is the processing of a data stream or an event stream, and by definition, data stream is unbounded data set, meaning infinite and ever growing. The new records keep on arriving, and this essentially fills the gap between the request response and the batching world, because this offers continuous and non-blocking processing of the data, and that is the reason why we went ahead with stream. And if you look at our main requirements, so we are looking at to have a windowed aggregation, that we aggregate all the events that we have received over a certain window. Right? It could be last 5 minutes or last 10 minutes or last 5 seconds for that matter, and we would like to support multiple aggregation windows, right? As in, for a counter which is in the range of 1 to 1000, we have to have an instant aggregation window, like in the order of less than 5 seconds or so. And for a counter which is greater than 100k, we are okay with the aggregation window in the order of minutes, right? Like mentioned earlier, the updates can we can aggregate, we can wait over the aggregations for some time and then maybe do the operation. And next comes the ease of configuration for new windows in future, right? Currently, we do have some configurations in place which are meeting our product needs at this moment, and uh, and we want to support the new requirements that might come our way, right? And triggers, basically, as a product, we want to send notifications to the user whenever their post crosses a certain milestone, uh, and this is for different engagement levels, right? And we want to solve that problem as part of these aggregations, given that uh, we are essentially solving the problem around updating the counters, right? And the system should also support the easy onboarding of new counters, new triggers, and new windows at a counter level in the future. So this is the high level architecture diagram. So each engagement event also has some business logic associated with it, and these events are captured by different services on the backend. And these backend services send events to our Kafka cluster, which is an in-house setup, right? And the reason why we have business logic associated, like at different services, is like we do capture and derive different internal counters also, which are helpful for us to understand better, and also helps in decision making in order to uh, show a post on a feed, right? And we do have different topics for different use cases, right? And we have this aggregation service running on Kubernetes. The similar blocks of aggregation service that are shown over here in the picture are denoting the n number of pods that we run, right? And the core logic around the windowed aggregations triggers are handled by the Kafka Streams API, as we are using the Kafka Streams domain specific language. And once the aggregations are done, we update that particular counter or the aggregated value in our key value store, which is ScyllaDB in this case, and also publish a change log to a Kafka topic back. So, I mean, so what is actually happening under the hood, right? So we are leveraging the features that Kafka has to offer, as in we don't have to worry about the messages or the events for a given post ID and a specific counter being processed in two different pods or instances. and this is taken care by the Kafka partitions, right? And we have the combination of entity ID, which is a post ID, and a counter as a partition key. And so, by definition of Kafka, these messages for a certain post ID and counter will always be in the same partition, and eventually will be processed by the same consumer. And Streams API. So we are using Kafka Streams domain specific language to handle most of the complex logic around the windowing and aggregations. Right? And any stream application, processing application implements and executes topology. And we define the topology as part of this aggregation service, like shown in the previous diagram. Topology is nothing but a DAG, a directed acyclic graph, and this topology involves a series of transformation that every event moves through from input to output, right? And at the end, we are updating the aggregated value in the DB. If you look at the topology that we have created, so moving from left to right, so we consume the events from an engagement topic. We do basic filtering operation on the event as to check if the counter is registered with the system or not. And if it is not, then we end up filtering them out and into a unregistered topic uh, for our monitoring and logging purposes. And we usually define the aggregation window on a particular range, right? Moving back again, moving from left to right, like any counter whose previous value is ranging from 100 to 1000 should be aggregated in the window of 5 seconds. And it is on this basis we further branch out the main event stream, like into different streams with different windows to aggregate over, right? And basically this we are deciding on the previous value of that counter that we usually get. And the three priority branches that you are seeing are basis the different aggregation windows. And once we branch them out, we are creating the different windowed streams out of them, right? And the aggregations will need to maintain a state around the events that are processed so far for the respective window streams. And handling a state has its own set of issues, like what if the instance or the pod shuts down or starts again or maybe replaced by another instance due to the rebalancing, uh, and all. So this is something that Kafka streams handle very well. This so-called local state is in memory, is stored in memory using embedded RocksDB, which also passes the data to the disk for quick recovery during restarts. And these state changes are also sent to a Kafka topic. So when a node goes down, the local state can be easily recreated. And we get an output stream for the aggregations, right? So basically, we are merging all those streams and then updating the aggregated values in the data store for the counters. Although we could have skipped this step, like we could also easily get away without merging the streams and then process them. It is the same thing at the end of the day. Also, we like after like updating the count, even before updating the counters in the sync, uh, we log the changes in a change log topic, right? So if we briefly look at some of the important pieces of the code, right? uh, in the first point, so we are essentially creating a stream object, and while creating a stream object, we need to pass the input topic which we are trying to consume from, the key value survey, which will be used for consuming the records out of the topic and deserializing them into input objects. Like mentioned in the previous slide, we branch out streams basis the aggregating window, which is the counter priority stream. And within that particular priority stream, we further group them by the key. Right? We are providing the key value survey for the serialization, and this returns a grouped string configured with key value survey. And we are looping over the streams at a particular at a priority or a window level. Right? After grouping them by the keys, we are defining a window for aggregation. Right? Uh, and this particular window is, again, if you can see, it is basically the seconds threshold, which is the window that we have mentioned. Right? And grace is a way of mentioning to consider out of order events that arrive after a mentioned threshold at the end of its window. And we went ahead with grace period as 0. And why did we go with grace period as 0? So we are looking at completeness versus duration to limit out the aggregation scope, and we are more concerned around the completeness of our data. Also, our events will never be out of order because we are using the wall clock time as the event time. I mean, if you again go back to the first point, the timestamp vector extractor that we have mentioned over there is internally using the wall clock time, which is a system time, and it is sort of guaranteed that events that we are processing are going to be in order. And it essentially boils down to the problem and the use case that one is solving. We were prioritizing completeness over the duration size, so we went ahead with grace as 0. Again, the first point in this slide, uh, like as mentioned earlier, the windowing aggregation requires maintaining a state and a local store where it will be maintained. Materialized is a store configuration object, and we are also assigning a name to it by appending the counter's priority level, which is the different windows that we have, and again provide it with key value survey for serializing and deserializing the results of the aggregation. The value aggregated is an integer, which is why we are using integer as the value survey. Right? Then we start on the aggregation. We'll split the stream into multiple tumbling windows and aggregate the events in that particular window. Right. As part of this, we also provide the supply interfaces to initialize and aggregate the counters. By default, the stream emits results whenever new results are available from the window. But we are only interested in the final aggregated value, which comes at the end of the window. So we send in this extra argument to suppress all the results, the values till the end of the window, and we are sending. So that is what we are sending, like suppressed buffer config, which is unbounded. So we are sending unbounded as a suppressed buffer config, which is unconstrained by size. And one has to use this suppressed configuration a bit carefully. If there isn't enough heap memory out there, we'd end up seeing some out of memory issues. And the result of the aggregation is a table with key and time window as the partition key, and the aggregation result as the value. So using toStream, we are again converting or turning the table back into the stream of events. After which we update the values in the DB. Right. So basically, we were able to see a 7:1 ratio on the events that we have received as an input and the writes that were happening on the DB, which is around 80% reduction and in the messages, which is sort of good for us. So we have solved the problem around using updates, multiple updates using Kafka streams and aggregations. Uh, However, we have reduced the write operations. We still have to serve this data to our end users, and the read scale is going to be in the order of 100 to 2k ops, and sometimes even goes beyond 300k ops per second. So we need a data store which could serve our needs with best latency numbers possible. Not that we had any major problem with the latency. It is just us looking for the best solution out there. Enter ScyllaDB. It is fast, right? So we are continuously seeing the sub-millisecond latencies uh, for this counters cluster, and not only that, we have better monitoring around the the database, right? So we have metrics visibility at data center level, cluster level, instance and shards, right? This gives us a better visibility and helps in pinpointing or understanding the issues around any abnormalities or maybe mishaps that were happening that were not according to our expectations, right? And also this is coming at a better cost. We have seen at least 50% reduction in the database costs with Scylla. And to put it in simpler terms, we think it is the best. So we are running a 3 node cluster for the engagement counters, and each node has a 48 vCPUs and 350 plus gigs of memory. And on the top of this particular image, we can see that the P99 latencies, P99 read and write latencies are in microseconds. Uh, and this is again with good amount of read ops on the cluster, read and write ops on the cluster. And the remaining part of the image shows that we have metrics at instance, shard level, right, where we can visualize which particular shards are taking in more load, and that helps in basically modeling and understanding the data. We tested the same similar setup and it was capable of serving 1.2 million ops per second, right? And how did we do it? We started replicating the events in a parallel cluster by creating a backlog of events, right? And we have seen even with the load touching 90%, the cluster is intact and there is no major impact on the latencies front. Here is the another screenshot, and this is during our cluster migration. Like we were migrating from the older database, which is not a ScyllaDB, to ScyllaDB, and this is during a migration job, which was exporting data from the previous store to ScyllaDB, and there were ongoing writes happening at this point in time, and you can clearly see that the load on each node is touching 100, and and when we validated the data across the two databases, we have seen what 99.999%, which is five nines match. Uh, that is how ScyllaDB has helped us a great deal in optimizing what we had earlier and then serving better, uh, in order to serve better to our end users, right? And we work in as a team, and this could not have been possible without the contributions from these bright minds from engineering, DevOps, and the leadership, right? And you can learn more about the operational challenges or the problems that we have encountered in our blog post, right? uh, and hosting engagement counters on ScyllaDB is one of our first and biggest bets for us, and we are in much of what this database has to offer, and this led to much great adoption of ScyllaDB in the organization. That's me. Thanks for tuning in. Thank you so much.